Good evening, everyone. Welcome back to the series of my video lectures on heat transfer. Today, we are going to review about our final exam in this video. Right. So, basically, you know that we have three topics: extended fins, extended surfaces or fins, then we have convection and dimensionless numbers, convection and dimensionless numbers. We have heat exchangers. So these three topics are for the final exam, and we are going to review three questions on from each topic. And you know that extended surfaces have made all the video lectures which are available online. You can view it. Convection and dimensionless numbers we have studied in class. Heat exchangers we have done pretty much in practical lab. So let's start away with the heat exchangers and let's see the first problem from heat exchanger. So let's see the problem. What is the given problem? The problem says, this is from heat exchangers by the way. The problem says a counterflow double pipe heat exchanger is to heat water from 20 degrees to 80 degrees at the rate of 1.2 kilogram per second. The heating is to be accomplished by geothermal water at 160 degrees Celsius, mass flow rate of 2 kg per second. The inner tube is thin walled and has diameter of 1.5. The overall heat exchange coefficient is 640 watt per meter square Kelvin. We need to find the length. Now the CP, the specific heat for both are given. Now let's see the problem. The hot water, the geothermal water, which is hot, is coming from this side and it's flowing out from this side, from this end. The cold water is coming in from this side and it's going out from the other side. Now you can see that temperature of hot water in is given to us, but temperature of hot water out, geothermal water, is unknown. We don't know the temperature that is coming out here, whereas temperature for cold water in is given and cold water out is also given, right? So this is the given data. So let's try to summarize the given data. Given, let's divide it into two parts. So we'll write about the hot water and cold water. Right. So we know the temperature in of cold water or simply water. So in water is 20 degrees. The temperature out of cold water is 80 degrees. The specific heat for cold water or simply water is 4.18 kilojoule per kg Kelvin. The mass flow rate of water is 1.2 kg per second. Right. For the hot water, we know the temperature in for geothermal water. So GW means geothermal water, that's the hot water. So in temperature is about 160 degrees Celsius. We don't know the out temperature. We need to find out temperature of geothermal water. We don't know. We know the CP of geothermal water. It's 4.31 kilojoule per kg Kelvin. We know the mass flow rate of cold water, of hot water, geothermal water, that is about 2 kg per second. What we also know is that the overall heat transfer coefficient is 640 watt per meter square Kelvin. We also know the diameter of the pipe is 1.5 centimeter or 0.015 meter, right? And apart from this, yeah, that's all we know. And we need to find the length. Length is how much, right? So pretty much that's a summary of the given data. That's all we have. Now, before we proceed, let's try to list all the formulae. Let's try to list the formulae here, which are applicable for the heat exchanger. Okay. Now, what we are going to do is we are going to use LMTD method, that is logarithmic mean temperature difference. Log mean temperature difference. That's the method that we are going to use in order to solve this problem. Now, for the log mean temperature difference, we have a set of formulae. So let us list from the basic formula. So Q is mass flow rate times Cp times delta T. Delta T logarithmic LMTD. From the formula sheet, you can find this formula. It's delta T1 minus delta T2 divided by ln of delta T1 divided by delta T2. Okay. Now it's pretty easy to find delta T1 and delta T2. The difference of these two sides. Now let us see what is delta T1 and delta T2. So let me erase this. So delta T1 lies geothermal water hot in and cold out. This is delta T1. The difference between this and this quantity here. And delta T2 is cold water in and hot water out. This is delta T. So T1 is here, this part, and T2 is the in. So this is in, this is out, this becomes T2, this is in, this is out, this becomes T1. Right? So that's delta T1 and delta T2. So let's write the formula for delta T1 is equal to hot water in, TH in, that is the geothermal water, cold water out, that's the normal water. And delta T2 is hot water out minus the cold water in. Right? And Q, as we all know, it is overall heat transfer times the area times the delta that we are calculating using LMTD method, delta T. We also know that area is pi times D times L. Yeah, and if you want to find L, it is area divided by pi times D. Now the whole purpose is to find L. Now look here, in order to find L, we need to know the area. I don't know the area. In order to find the area, you should know Q, then we can find the area. In order to find Q, we are going to use this formula, right? Also, I should know delta LMTD in order to find the area, because that's also unknown. So we have two quantities there. So step 1, let's find Q. So Q of cold water, or simply water, is mass flow rate of water times Cp of water times delta T of water, that is delta T of in minus out. Okay. That's a cold water. So mass flow rate is somewhere about 1.2, I believe. Yes, the mass flow rate is 1.2. So this is 1.2. Cp of cold water is somewhere about 4.18. So 4.18. Delta T, in minus out. So inlet and outlet are given here. 80 minus 20. that becomes 60. 80 minus 20. So if you plug in all the numbers, you will get somewhere about 301 kilowatt. We all know that heat transfer Q of W should be equal to Q of geothermal water, and these both quantities will be equal to 301 kilowatts. Right. Now if you look at the formulae, I know the hot water in, I know the cold water out, I know the cold water in, but I don't know the hot water out. This quantity is unknown. We need to find that quantity. Step 2, Q of geothermal water is mass flow rate of geothermal water times Cp of geothermal water times delta T of geothermal water. So mass flow rate, now Q remains the same, it's 301. Mass flow rate is 2, Cp is 4.31, delta T is T out of hot water minus T in of hot water. T in is known to me, that is 160 degrees Celsius. T out is a question mark. If you plug in all the numbers and solve, you should get T out at 125 degrees Celsius. That's what we get. Right. So let's go back and write here. Now I have determined the out. It's 125 degrees Celsius. Degrees C. Right. So pretty much we are good to proceed forward. We have all the data. So step 3, we are going to calculate delta T1. So delta T1 is T of hot water in minus T of cold water out. So this is 160 degrees Celsius minus 80. We should get 80 degrees Celsius. Step 4, we are going to do delta T2. It's T of hot water out minus T of cold water in, and it should give you 125 degrees, that's the out, minus 20 degrees, that's the cold water. This should give you 105 degrees centigrade. Step 5, delta LMTD. Delta T LMTD, log mean temperature difference, is, let's take the formula from the formula list we have listed here. T1, delta T1 minus delta T2 divide by ln of T1 by T2. So delta T1 minus delta T2 is 180 minus 105 divide by ln of T1 by T2, 80 by 105. So this should give you, let us calculate how much is the answer. So 80 minus 105 should give you minus 25 divide by ln of 80 divided by 105 should give you minus 0.2719. If you divide, the negative sign gets cancelled. So 25 divided by 0.2719 is 91.94. That's what we are going to get delta LMTD, right? Then step 5, we are going to calculate Q is equal to overall heat transfer U times area times delta T LMTD. So I know Q, I know U, I know delta LMTD. So area is Q divided by U times delta LMTD, delta T LMTD. So Q is 301 divided by U is overall heat transfer. How much we have? U 640. So we have U as 640 So let's write it here, 640, and delta T LMTD is 91.94. So you calculate, you should get somewhere about 5.12 square meters. Now that's the answer in the presentation, but in reality we are getting 5.12 to the power minus 10 to the power minus 3 meters square, right? Just check as of now. I'll go with the answer with the presentation, but the real answer is 5.12 into 10 power minus 3. Because if I consider 10 power minus 3, then the length is going to be too small, so I'll consider 5.12. But in the exam, please make sure that whatever number you get, use that number. Don't worry about the answer. Step 6. Area is equal to pi times d times L. L is equal to area divided by pi times d. So area 5.12, as I said, I'm going to use 5.12. It's actually into 10 power minus 3, but if I use 10 power minus 3, the length is going to be too small. So 3.14 times diameter is 0.015. If I calculate, I'm going to get the length of 109 meters. So length is 109 meters. That's the answer. That's a required length for the heat exchanger to get to transfer 301 kilowatts of heat between the hot and the cold water. That's a length that is required. I hope that was clear. So follow this method and please check this answer. You should also get 5.12 into 10 power minus 3, and the length will be again 109 into 10 power minus 3. So pretty much 10 power minus 3 is missing in the slide, so that's a typo, right? Alright, so that's pretty much what we do with the heat exchangers problem. I hope it was clear. The next topic that we were we would like to review is the convection and the dimensionless number. So we have here convection and the dimensionless number. This is the topic that we are going to review. So let's read this question. A 6 meter long section of 8 centimeter diameter horizontal hot water pipe in the figure passes through a large room whose temperature is 20 degrees. So that's T infinity. If the outer surface temperature of the pipe is 70, determine the rate of heat loss from the pipe by natural convection. Use the appropriate equation to calculate the Nusselt number. Now we have the formula sheet. We can find all the formulas in the formula sheet. So if you open the formula sheet, page number 1, 2, 3, page number 3 and page number 4 and page number 5 give you all the formulae for Nusselt number, right, with regards to Rayleigh and all. So let's try to solve this problem. Let's write the given data, what is given to us. So let's copy the given data. So the given data includes the length of the pipe, right? The length of the pipe is how much? 6 meters. So the length is 6 meters. The diameter is 8 centimeters. So the diameter is 8 centimeters. That is 0.08 meter. Then we have room temperature T infinity, which is at 20 degrees Celsius. If the outer surface temperature, so we have Ts, which is at 70 degrees Celsius, and we need to determine the rate of heat loss Q is how much, right? So that's the question. As I told you in the class, we need to refer to the air table for the properties of air at given temperature. So let's, from the air table at 1 atmosphere, now I need a temperature point. So I'm going to take the average of these two temperatures. So T average is equal to T infinity T surface plus T infinity divided by 2. So T surface is 70, T infinity is 20 divided by 2. So this is 45 So I'm going to refer A tables 45 at 45 and 1 atmosphere. In the exam, as I see, I think you might be given A tables or you might be given the properties directly. But in order to read, please follow the instructions that I gave you in the class. The A tables are also available on Moodle. You can download and check. At 1 atmosphere, 45 degrees centigrade, you will find that the density is 1.109 kilogram per meter cube. Specific heat is 1.007 kilojoule per kg Kelvin. Right. Kinematic viscosity is 1.750 into 10 power minus 5 meter square per second. Dynamic viscosity mu is dynamic viscosity is not given, should be there in the table. So let's take another parameter, that's K. Thermal conductivity is 0.02699 watt per meter Kelvin. Even dynamic viscosity we can calculate from kinematic and density because both are known to us, so we know the relation. Prandtl number PR is 0.7241. Coefficient of thermal expansion beta is 1 over T, that is 1 over, now T, look here, we know the T average, so T is 273 plus 45, that should give you 318 Kelvin, so that is 1 over 318, so we get 3.145 into 10 power minus 3 Kelvin per Kelvin. So coefficient of thermal expansion, as I explained in the class, you take a metal pipe, heat it from one end. The pipe has original length L. It expands on heating, and now we have a new length L final. Right? So the change in length varies from material to material, and that depends upon coefficient of thermal expansion. Right? So coefficient of thermal expansion varies when the material changes. In this particular case, we have beta. Now this is for air, by the way, since it's air table. More or less, the concept is almost the same. Okay, anything expands upon heating. Air also expands upon heating, right? So it's the same concept. That's a short meaning of coefficient of thermal expansion. Okay. Coming back to the problem, let's list some of the numbers that we are going to use. So let me try to sort the page here. So the first step one, we are going to calculate the Grashof number, GR, Grashof number. Now remember that Grashof number tells us whether the flow is laminar or turbulent. That's the information we get. So it's gravity times coefficient of thermal expansion times T surface minus T infinity times d cube divided by v nu square, that is kinematic viscosity. So this is kinematic viscosity, diameter of pipe, coefficient of thermal expansion 9.81, surface temperature, room temperature, right? So let's plug in all the numbers. What do we get? 9.81 times 3.145 into 10 power minus 3 times Ts is 70 minus T infinity is 20 times the diameter is 0.08 cube to the power 3 divided by kinematic viscosity is 1.75 into 10 to the power minus 5 square. Now if you plug in all the numbers, we'll get somewhere about 2581135.2. That's the Grashof number. So it's pretty clear that from Grashof number the flow is laminar, because you see, if Grashof number is greater than 10 power 8, it is turbulent. It is less than 10 power 8, I believe, or 6, I believe. Let me check Grashof number. Yeah. So it's 10 power 6. It is less than 10 power 6. It becomes laminar. So let us check. That's 1, 2, 3, 4, 5, 6, 7. So this is 0.2 into 10 power 7. That's less than 10 power 8. So the flow is definitely laminar. Next, step 2. Let's calculate the Rayleigh number, Ra. Rayleigh number is Grashof number times Prandtl number. Prandtl number we got it from A table. Grashof number we have calculated. So if I calculate 2581135.2 times the Prandtl number is 0.7241. If you multiply both, we are going to get 1.867869 into 10 power 6. That's the Rayleigh number. Remember this, all these are dimensionless numbers, right? Now, based on the Rayleigh number and based on the Reynolds number too, we can calculate, we can get the Nusselt number. Now, if you see the list of formulae that is given to you in the PDF that has been emailed to you, so you will find page number 4, I believe. Yeah, 4. Page number 4. Page number, 1 second, 1, 2, that is RA power 1.6. So RA 1.6.4. That's precisely the number, 0.6 plus. So 1 minute page. Yeah, page number 5. Page number 5, horizontal cylinder, that is the second row. You will find the Rayleigh Nusselt number and with regards to the Rayleigh number, right? What is the criteria? Look, if the Rayleigh number lies between 10 power 4 to 10 power 7, as mentioned in the page number 4, or 10 power 7 to 10 power 11, or 10 power 5 to 10 power 11, okay, and we have very much the condition of horizontal cylinder because it's a pipe, so it's horizontal. Nowhere it is mentioned that it is vertical. So we are going to use this Nusselt number, which is on page number 5, because our Grashof, our Rayleigh number is between the said quantity, that is 10 power, it lies between 10 power 4 to 10 power 7. We have in the order of 10 power 6. So we are very much safe, and we can use this Rayleigh number, this Nusselt number, which is the horizontal cylinder. So let's write down the equation of Nusselt number from page 5 in the formula sheet. We have the Nusselt number Nu. Why I am choosing that particular number? Because the case is of a horizontal pipe, which is similar to our case. That's 1. And the Rayleigh number that I have, that I calculated, that is 1.89 into 10 power 6, lies between 10 power 4 to 10 power 7. So these two conditions are satisfied. Hence, I am going to use the Nusselt number Nu equal to 0.6 plus 0.387 times the Rayleigh number power 1 over 6 divided by 1 plus 0.559 divided by Prandtl number PR to the power 9 over 16 to the whole power 8 over 7 to the whole power 2. Now if you plug in all the Rayleigh and the Prandtl number, we get the Nusselt number, and it's it's 17.4. That's the Nusselt number I have. Now Step 4. For general convection, the Nusselt number is H times D divided by K. Now if I want to calculate, I should calculate H, but because that is required for my heat transfer calculation, so H is equal to Nusselt number times K divided by the diameter. So I have K value from the A table, I have diameter that is given to me, I have calculated the Nusselt number, plug in all the numbers, that is 17.4 times K is 0.026999, divided by 0.08. If you calculate everything, you get H at about 5.87 watt per meter square Kelvin. So that's H, right? So I got H. Now I know that the heat transfer Q is via convection. So I know the formula, H times surface area times the difference in temperature. So H is known to me, area is known to me, delta T is known to me. Area, by the way, is pi times D times L. So 3.14 times the diameter 0.08 times 6, that is equal to 1.508 meter square. Now if I substitute everything, Q is equal to, delta T is, by the way, difference of, so let's take delta T also. So dt or delta T is T surface minus T infinity, that is the average, minus T infinity, get average surface. Okay, so that is 70 minus 20, that's what we get, 50. Now I have all the numbers, delta T, surface area, and H. So if I want to calculate Q, plug in all the numbers, and Q should be around 442.6 watts. That's how we calculate Q. Now let's summarize this particular problem. If you see the formula of Q, that is H times area times delta T or dt. Now area is known to you, delta T is known to me. My aim is to calculate Q, but what I don't know is H. This part, I don't know how much is H. H is unknown. This is okay, this is okay, this I have to calculate H, I don't know. Now in order to calculate H, I need two numbers. First, I need Grashof number, I need Rayleigh number, I need Prandtl number from the interval. So Grashof from the formula, Rayleigh, again we have the Grashof times Prandtl, and Prandtl from the A table, right? I need these three numbers. Then depending upon the Rayleigh number from the formula sheet, I am going to choose the formula for Nusselt number. I am going to calculate Nusselt number. Once I have the Nusselt number, I am going to use the general convection equation, that is H times D divided by K, wherein I can calculate H from here, Nusselt times K divided by D, and that's how I can then substitute it back here to get the value of Q. So these are the required steps in order to get H and in order to get the value of Q. I hope it is clear. The following next part of the video, I'll be discussing question number 3, which is from the extended surfaces, and then I'll be giving you some idea about extended surfaces too. Thank you.